fact that you compute the dot product of the input vector and the parameters in the perceptron. Now the parameters in the perceptron are the connection weights and the threshold value. Okay. So now when we want the perceptron to compute a function, we would like the weights and threshold value to be fixed for computing that function. Okay. Now we have also seen a training algorithm. We have also seen a training algorithm by which the data one after another comes in, and then the weight values are changed according to a particular algorithm. The algorithm is that if there is any failed vector, then we add that failed vector to the weight, and eventually the algorithm will converge to the correct set of weights to be able to compute that function. Okay. So now perceptron training algorithm is something you will have to implement in the lab, and you will be evaluated based on your implementation and understanding of the algorithm. Okay, how it works for linearly separable functions and non-linearly separable functions, how it works for threshold functions, what is the role of the initial value, and so on. Okay, so please pay attention to the perceptron training algorithm, which we have been saying like A star is one of the pillars. So today we would like to do another conceptual thing, which is what is the reason that perceptrons have limited computing power? Okay, what decides that computing power? Now we know this perceptron rule that sigma wi xi, which is the dot product of the weight vector. Now theta is also a weight which is absorbed as a weight with a fictitious input of -1. So that weight vector and the input vector, their dot product is taken and compared with theta, the threshold. Now compared with 0. Now we know this that the number of threshold functions reduces drastically compared to the number of possible Boolean functions. Number of Boolean functions is a very small part of the whole whole set of functions which are computable, and the threshold functions seem to be still a small part of that space of Boolean functions. Okay, so now we would like to ask why is it that if the number of inputs is 2 and the number of Boolean functions is 16, possible functions is 16, why is it that the number of threshold functions is 14? Okay, what decides that number of threshold functions? So to do that, we would like to discuss this point of perceptrons and their computing power. So this is a conceptual discussion, and let us see how to go about this. Okay, what decides the computing power? So we have seen this table here. For 4 inputs, the total number of Boolean functions possible is about 64,000. Out of that, only 1,008 are computable by a perceptron. So now, to understand this, we have to first get hold of another concept called concept of hyperplanes. So now we compare sigma wi xi, the dot product of the weight vector, and the input vector with theta. So sigma wi xi equal to theta defines a linear surface in the w theta space. Okay, so if there are only 2 inputs for a perceptron, then w1 x1 plus w2 x2 equal to theta is a plane in a 3-dimensional space, which is w1 w2 theta space. Okay, there is a 3-dimensional space. There are 3 coordinates, w1, w2, and theta. Now, so in the w theta space, sigma wi xi equal to theta defines a linear surface. Okay, where w equal to w1, w2 up to wn is an n-dimensional vector. A point in this w theta space defines a perceptron.
Theta is not part of the diamond.
Okay, so if theta it becomes another axis, then we have homogeneous equation. So we have sigma wi xi minus theta equal to 0. Yeah, and that of course will only tilt. It will not translate. It will pass through origin. Yeah, you're right. That if we have only W1, W2 as the plane, then theta will translate the hyperplanes. Yes. Yeah, that's an important point. So we have to deal with homogeneous equation. So we observe theta as another weight and as another coordinate in the space. So a point in this W theta space defines a perceptron. Okay, so every point defines one W1, W2, and theta value, and that corresponds to a perceptron. Okay, what function it computes? That depends on where this point is placed. Okay, so we'll understand this going forward. Now, two perceptrons may have different parameters, but the same function. Okay, we know that for AND function, infinite number of W1, W2, and theta values are possible. They just have to satisfy some constraints in the form of 4 inequalities. Okay, so one of the constraints is that if x1 and x2 are both 0, then we know that 0 should be less than or equal to theta. So which means theta is greater than or equal to 0. So this is a hyperplane in the W1, W2 theta space. Okay, and this is one of the constraints which needs to be satisfied for computing AND. Right. So the example of the simplest perceptron is what? It is a perceptron with a single input where the weight is W and the threshold is theta. Okay, so this perceptron, what can it compute? Let us see. It can compute these 4 functions: the true function, the false function, okay, or the 0 function, identity function, and the inverse or the complement function. So let's see, these 4 functions, how are they computed? So for x, we know that x can take only 2 values, 0 and 1. The first function is called the 0 function, for which whatever be the input, the output is 0. Okay, so let's see what constraints need to be satisfied to compute the 0 function. If x is 0, then we know that w into 0 should be less than or equal to theta. Okay, sorry, this needs to be corrected. Should be less than or equal to theta, which means theta should be greater than or equal to 0. Okay, this is one constraint. And if x is 1, then w should be less than or equal to theta again. Okay, so theta greater than or equal to 0, w less than or equal to theta will compute the 0 function or the false function. Okay, and infinite number of possibilities exist for w and theta. Let's take the identity function. Okay, for identity function, if x is 0, y should be 0. If x is 1, y should be 1. So if x is 0, then we again get the condition theta should be greater than or equal to 0. If x is 1, w into 1 should be greater than theta for y to be 1. Okay, so theta greater than or equal to 0, w greater than theta will achieve the identity function. Okay, y will mirror x. Then we have the complement function, the inverse function. If x is 0, y is 1, x is 1, y is 0. So if x is 0 and y should be 1, then we know 0 should be greater than theta, implies that theta should be less than 0. And if x is 1, y should be 0, implies that w should be less than or equal to theta. So this is the inverse function. For the one function, a true function, if x is 0, y should be 1. If x is 1, y should be 1 again. If x is 0, then theta should be less than 0. Okay. And if x is 1, y should be greater than theta. So these constraints on theta and w achieve these four functions. Okay. Now let's see this geometrically. So for a perceptron with single input, w dot x equal to theta is the defining hyperplane. In this case, w equal to theta is a line in the w theta space. Okay. So plot w in the x-axis and theta in the y-axis. So now there are, when x is equal to 0, theta equal to 0, so x-axis is giving one hyperplane for x equal to 0. And when x equal to 1, w equal to theta, which is a line passing through the origin at 45 degree with the x-axis. So first and foremost, inputting the value of x in wx equal to theta gives me the number of hyperplanes possible for different values of x. In case of a perceptron with single input, the number of hyperplanes possible is 2. There are 2 lines. Now, the 2 lines, by intersecting, how many regions can they produce? They can produce 4. That's why only 4 functions can be computed by a perceptron with a single input. Okay. How? So let's see the conditions for computing different functions. The false function or 0 function needs the condition theta greater than or equal to 0 and w less than or equal to theta. So theta greater than or equal to 0, theta greater than or equal to 0 is this whole half region here. Okay, everything above the x-axis. And w less than or equal to theta is the whole set of points below this w theta line. So what is the region which satisfies the condition of theta greater than or equal to 0 and w less than or equal to theta? It is this region F1. Okay. And any point picked from here, which will define a perceptron, because every value of w theta defines a perceptron, any point picked from here will compute the 0 or false function. No other w theta can do so. Okay, so this explains why the regions produced by the hyperplanes are important for the computing capability of the perceptron. Now let's see the other functions. Identity function requires theta to be greater than or equal to 0 and w to be greater than theta. Theta greater than or equal to 0 is the region above the x-axis. And w greater than theta is the set of points above this 45 degree line. So this region F2 will compute the identity function. So false function is computed by F1. Identity function is computed by F2. What about complement function? Theta should be less than 0. W should be less than or equal to theta. F3 region satisfies this condition. F3. W should be less than or equal to theta. I think it is this region, right? Theta should be less than 0 and W should be less than or equal to theta. It is this region, sorry. So this F4 should be F3, make that correction. And F3 should be F4. Okay, so you see, this is what is achieved. Let me make the correction right. So Independent of these details, what you should be noting is that there is a one-to-one correspondence between the number of regions produced by the hyperplanes obtained by plugging in values of x, okay, and the number of functions computable by a perceptron. Okay, so this gives rise to a very important fundamental observation. The number of threshold functions computable by a perceptron is equal to the number of regions produced by 2 to the power n hyperplanes obtained by plugging in the values x1, x2 up to xn in the equation sigma wi xi equal to theta I goes from 1 to n. Okay, this is called the fundamental observation for the computing power of perceptron. When were such observations made? In 60s and 70s. Okay, and this has remained absolutely critical for the field of neural network-based computation, deep learning everywhere. Okay, since we know that the computing power of a perceptron corresponds to the number of regions produced, this generalizes. The number of regions produced by a neural network through the interaction of the hyperplanes produced by individual neurons. The number of regions produced by that contributes to the computing power. Okay, and now that we know that deep neural networks have millions and billions of parameters, which means the weight values, which means millions of neurons. It is the number of neurons which is giving rise to very complex assembly of regions produced by the intersection of hyperplanes, and that is giving rise to the computing power. Okay, as the number of neurons increases, the computing power also increases. But we are discussing only one neuron, which is the perceptron. Okay, so any question on this observation? Yes, the point that the number of regions produced gives rise to the computing power, not only for one perceptron, but the whole assembly of perceptrons also. Okay, what is the question? Coming to that. The question was about the number of threshold functions and is there a closed form expression? We are coming to that. Now, let us ask, why is it that two input perceptron, theta and W1, W2, computes only 14 regions, only 14 functions? Is it that the maximum number of regions produced by hyperplanes is equal to 14? Yes, this indeed is the case. Let us see. Let's remember how the Boolean functions are loaded onto the perceptron. Yeah. So x takes values 0, 0, 0, 1, 1, 0, 1, 1. And the AND function is computed by satisfying these linear inequalities, theta greater than or equal to 0, W2 less than or equal to theta, W1 less than or equal to theta, W1 plus W2 greater than theta. Okay. So let's begin to think recursively. M linear surfaces called hyperplanes. Each hyperplane is of d minus 1 dimension in d dimension. Then what is the maximum number of regions produced by their intersection? Okay, this is the question we are asking. If there are m linear surfaces called hyperplanes in the d-dimensional space, now each hyperplane will be of dimension d minus 1. right? So if there is a two-dimensional space, then the one-dimensional hyperplane is the line, okay? And the line has the dimension of d minus 1, which is 2 minus 1, 1. Okay? So any hyperplane in the, note this carefully, any hyperplane described on a d-dimensional space defines itself a space of dimension d minus 1. No? So in a three-dimensional space, the hyperplanes are two-dimensional planes. On the plane, the number of dimensions is 2, 3 minus 1. Okay? So the number of regions produced by the intersection of m linear surfaces in d dimension, let's denote this as R, M, D. Now to ground our observation, let us see let us see what to do about the number of computable functions by a neuron which has two inputs. So for a neuron with two inputs, the weights are W1, W2, and the threshold is theta. The defining equation is W1 x1 plus W2 x2 equal to theta. Okay. Plug in the values, 4 possible values of x1 and x2. x1 equal to 0, x2 equal to 0, then we'll get theta equal to 0, which will define a plane P1 in the W1, W2 theta space. Okay. x1 equal to 1, x2 equal to 0, x1 equal to 0, x2 equal to 1, W2 equal to theta will be the plane P2. x1 equal to 1, x2 equal to 0, W1 equal to theta will be the plane P3. x1 and x2, both being 1, will give rise to the plane W1 plus W2 equal to theta, which is P4. All clear so far? So 4 hyperplanes in the three-dimensional space of W1, W2 theta. These are homogeneous hyperplanes. They all pass through origin. Okay. Now let us count the number of functions which can be produced by the neuron. We'll begin to, so this you have to note very carefully. We begin to produce regions by bringing in one plane after another. Okay. If you are working on something else in the class, or if you are talking, please stop all that and pay attention to this particular point, this very point. Okay. Maybe you close your laptop. So we have seen that there are 4 hyperplanes in the three-dimensional space. There are 4 planes, P1, P2, P3, P4, obtained by plugging in x1 and x2 values. I bring in P1. So that will produce 2 regions. P2 now comes in. And it is intersected by P1 in a line. Okay. So 2 more new regions are produced. 2 more new regions where? 2 more new regions in P1. Okay. Which is giving rise to 2 more new regions in the whole space. Okay. After P2 came in, it produced a line on P1. It produced 2 regions on P1. And that gave rise to 2 more regions in the space. Now, therefore, it is 2 plus 2 equal to 4. P3 now comes in. And how many regions are produced on P3? Okay. Notice that we are not worried about the number of regions produced in the space. That will automatically result from the regions produced in the new plane which is coming in. So P3 has come in. P3 is intersected by P1 and P2 in 2 intersecting lines. So 4 more regions are produced on where? On P3. And these 4 more regions are added to 2 plus 2, which is 4. 4 plus 4, 8. Okay, 8. Last plane comes in. This is P4. P4 is intersected by P1 to produce one line, by P2 to produce another line, and by P3, another line. So 3 intersecting lines. 3 intersecting lines can produce how many regions? At most, 3 intersecting lines. 6. Okay. So we have then 8 plus 6, which is 14. Okay. And whatever you do, a perceptron with 2 inputs cannot compute more than 14 functions, 14 Boolean functions. And we know that XOR and XNOR cannot be computed by a perceptron with 2 inputs. Okay. And the other 14 will be computed. And this is also proved by this discussion on number of regions produced. And I don't know if you knew that in a 3-dimensional space, 4 hyperplanes or 4 planes can produce only 14 regions at most. Did you know this? If you knew, then that's very good. And you would be able to answer the question, how many functions can be produced by, computed by a perceptron with 2 inputs? How many functions can be computed by a perceptron with 3 inputs? We know it is 128. Okay. And if you argue this way, that in a 4-dimensional space with W1, W2, W3, and theta, the 3-dimensional hyperplane by intersecting will produce only 128 regions. So that will be the answer to the number of functions computable by the perceptron. Okay. So this is nice. And do you have any questions here? We'll have a general formula also for M hyperplanes in D-dimensional space. Any question? Okay. If there are no questions, then let us also have a geometrical understanding of why XOR is not computable by a perceptron. So you see the 4 points which we are interested in are 0, 0, 1, 0, 1, 1, and 0, 1. Okay. For XOR, this 0, 1 belongs to the positive class, 1, 0 belongs to the positive class, 0, 0 belongs to 0 class, 1, 1 belongs to the 0 or the negative class. Okay. So diagonally opposite points belong to 2 different classes. And you can see that there is no way a line can separate both the positive points from the negative points. There is no way. The diagonally opposite points belong to one class. The opposite diagonal points belong to the other class. And one single line cannot separate them. Similarly for X0. Can and be separated? Yes. 1, 1 belongs to the positive class. 1, 0, 0, 0, 1, 1, 0, 1 belong to the negative class. So you draw a hyperplane here, draw a line here. The positive class gets separated from the negative class. Okay. Right. So, so XOR cannot be computed. Then what can we do? Okay, we'll have to think of some way of doing this. We're coming to that. Okay. So while we have theoretically proved by means of counting the number of regions that XOR, XNOR, only 14 can be computed, we have also demonstrated by geometry as to why this is the case. Okay, so this very fundamental observation is the heart of deep learning. It is the heart of deep learning and neural network based computation. This. So let me repeat this point one last time and then move to other things. The number of threshold functions computable by a perceptron is equal to the number of regions produced by 2 to the power n hyperplanes obtained by plugging in the values x1, x2 up to xn in the equation sigma wi xi equal to theta I goes from 1 to n. Now, if you, a bit of digression. Now, if you say that in this era of new method of doing AI, large language models, generative AI, transformer, ChatGPT, why should we worry about results found out in 60s and 70s? Should we care about them? The answer is a very, very emphatic yes. Okay. Okay. Because these 60s and 70s was pointing to the fact that do something about increasing the number of regions by intersecting hyperplanes. Okay. And the way was not known. Okay. In 1980s came multi-layer perceptrons, where more than one perceptron were put together and larger assembly of perceptrons and layers of perceptron got created, thereby giving rise to a much larger computing power. And the hint for doing so was in this result, in the fundamental observation result. Okay, so it is important to know these things because that points to the direction forward. So anybody wants to ask, why should we worry about these fundamental points? Okay, you are welcome to criticize, comment, question, anything that we do in the class. Okay, so if you do not do if you do not have a strong foundation, there will be a problem going forward. Okay, the pyramid's base has to be very strong. Okay, now we would like to look at the derivation of the number of regions produced by hyperplanes in d-dimensional space. The number of regions founded by n hyperplanes in d-dimensional space passing through the origin because theta has been absorbed as a weight, is given by the following recurrence relation. Now, this recurrence relation you can understand very easily if you had followed how we derived the number 14, okay, for 3 planes coming in the three-dimensional space. Let R and D be the number of regions produced by n hyperplanes in the d-dimensional space. It is equal to Rn minus 1, comma D, which is the number of regions produced by n minus 1 hyperplanes in the d dimension, plus the extra regions on the nth hyperplane produced by existing n minus 1 hyperplanes. Okay, which must be equal to Rn minus 1, comma D minus 1. So this is a recurrence relation. Rn comma D is equal to Rn minus 1 comma D plus Rn minus 1 comma D minus 1. So for the fourth plane coming in the three-dimensional space, the number of regions produced by 3 planes already in the space plus the number of regions produced on the fourth plane by the existing 3 planes, which was equal to 6, if you remember. So this is a recurrence relation, and recurrence relation must have boundary conditions. There are two parameters here, n and d. Therefore, you need 2 boundary conditions. The first boundary condition comes from making n equal to 1. The number of regions produced by one hyperplane in D dimension must be equal to 2. And the number of regions produced by n hyperplanes in one dimension, okay, is also equal to 2. Because all are passing through origin. And in one dimension, the space is a line. Okay, so all the endpoints are on the origin. They produce two regions. So the two boundary conditions have been laid out. R1, D is 2, Rn, 1 is 2. Now this recurrence relation is solved by the method of generating functions, okay, which we will do in the next class. Okay, this generating function is little complex. Okay, see the form of the function. Fxy is equal to n equal to 1 to infinity, d equal to 1 to infinity, Rn, d x to the power n, y to the power d. So we are interested in the coefficients of this generating function Rn, d. And as you know, from the recurrence relation, we'll get this kind of constraints. Rn, d minus Rn minus 1, d minus Rn minus d minus 1 is equal to 0. Okay. And Rn minus 1, d corresponds to shifting n by one place, multiplication by x. And Rn minus 1, d minus 1 corresponds to shifting n and d by one place each, multiplication by xy. So on expanding fxy, we'll get some expression. And we go ahead with the expansion. And after all this expansion, by equating coefficients, we get Rn, d is equal to 2 into I equal to 0 to d minus 1, ci n minus 1, where c is the combination. Okay. The number of ways I things can be chosen out of n minus 1 things. Okay, we'll derive this slowly and rigorously. Okay, the steps are here. We'll do that. So let's end the class by remembering what we did in the last class. We did perceptron training algorithm. Do please remember that perceptron training algorithm requires some pre-processing. Theta is absorbed as a weight. And then equal to test is removed. Then all the zero class vectors are negated. Okay. When we do so, we start the algorithm by initializing the weight values. The number of steps taken to converge depends on the initial value and also on the choice of the vectors at each step that we pick up for testing. And the test for w dot xi greater than 0 should be succeeding for each vector. Then we get the required w vector. So we ran the algorithm on the NAND function, and we found that after some 10-15 steps, we could get the W value. So this will surely happen. And as the dimension of the perceptron increases, the number of inputs increases, the number of steps taken also increases. Okay. So this shows the reason for the training algorithm to take more time as the size of the problem increases. Now, is there any theorem there, any kind of NP hardness, NP completeness result? It turns out that that is the case. In late 90s or early 2000, it was proved that training of a feed-forward neural network is NP hard. Okay, I'll do that proof in the class. By the way, was NP completeness, NP hardness done in any of the classes before? NP completeness, hardness? No. Sure. Okay. And the convergence proof of perceptron training algorithm is also very elegant. we considered this function wn dot w star divided by mod of wn. We understood that GWN is upper bounded, since the assumption is that the vectors are coming from a linearly separable function. There must be a W star, okay, which does the separation. So GWN is upper bounded by the mod of W star. And we saw that wn dot W star, which is the numerator, that increases linearly with n, the number of iterations. So if n becomes infinite, which means perceptron does not converge, then the numerator will become infinity. We also understood that the denominator also increases, but it increases at root of n. Actually, this square root sign extends over the whole expression. Square root of n. So the denominator also becomes infinity, but at a much slower rate. So in the limit, the ratio will tend to infinity. Okay, if both were increasing to infinity at the same rate, then we would need some other machinery. But since the numerator is increasing at a faster rate, then GWN would become infinity as n tends to infinity. But GWN cannot be infinity. It is upper bounded by W star. Okay, therefore n cannot be infinity. That means the perceptron training algorithm has to converge if the vectors are coming from a linearly separable function. Okay, so these are the important things we did, and a number of a number of discussions are being done, which will help you appreciate things when you do courses in machine learning, especially deep learning and neural network based learning. Okay, you will remember these basic points. So I'll end here today, and in the lab you will have to implement perceptron training algorithm, backpropagation algorithm, which I'll do next week. And in today's lab, you will continue implementing A star for missionaries and cannibal problem. And those who finish that should implement AO star, run it on tic-tac-toe. AO star has not been covered in the class. You are supposed to learn this, okay? And there will be Viva and discussion on the code in your last lab. Also input-output examination by the team. Okay.